All right, welcome back. So at this point in Unit 3, we have a good understanding of MOS electrostatics in one dimension. But it's actually, MOSFETs are actually 2 or 3 dimensional devices. We need to understand what the influence, primarily of 2-dimensional electrostatics, is on MOSFETs. So we've been discussing MOS capacitors by drawing energy band diagrams in a direction normal to the structure, normal to the silicon surface. But there is also a variation in potential along the surface. So the potential is varying in 2 dimensions. And this can have an important effect on MOS transistors, usually a detrimental effect. I became aware of this myself. My first job after college in the mid-1970s was to develop a I joined a team that was developing a 5-micron N-channel MOS process. 5 microns was the point at which 2D electrostatics began to bite us, and we began to encounter things called short channel effects, which were all brand new to us, and which had to be understood, and we had to learn how one controls these effects in order to produce good transistors. And as channel lengths just got shorter and shorter, the role of 2-dimensional electrostatics became more and more important, and it continues to be extremely important. So let me just begin by describing from a terminal characteristic what the influence of 2-dimensional electrostatics is, and then we'll try to go inside the device and see if we can understand why it has this influence. So we've seen some of these effects. This is a transfer characteristic of an MOS transistor at low and high drain voltages. And we've seen that if we focus at some particular current, that the characteristics are shifted. That corresponds to a shift in threshold voltage and increasing threshold voltage a decreasing threshold voltage with an increasing drain voltage. That's an effect of 2-dimensional electrostatics. Now, a similar effect will occur if we did a characteristic at one channel length and then did the same characteristic at the same drain voltage at a shorter channel length. We would also see this reduction in threshold voltage. That is also a consequence of 2-dimensional electrostatics. So the threshold voltage and dibble increases as we scale the channel lengths down. Now, another effect you can see is that you may encounter transistors where you don't just have a shift of the characteristics, dibble, but you also have a change in the subthreshold slope. This is another consequence of 2-dimensional electrostatics. So that might happen when you increase the drain voltage. It might happen when you decrease the channel length at the same drain voltage. In severe cases, the device will punch through, and we will explain what punch through means. Okay, and a third consequence of 2-dimensional electrostatics has to do with the output resistance of the device when we plot the IV characteristics as output characteristics, output current versus output voltage. We know that an ideal MOSFET should have 0 slope in the saturation regime. Real MOSFETs have finite slope. That slope increases as the channel length decreases. Or another way of saying that is that the output resistance increases or decreases as the channel length decreases. So all of these are consequences of 2-dimensional electrostatics that we want to understand and control if we're a device designer. So what that means is we need to solve the 2-dimensional Poisson equation. Divergence D is equal to rho. We know that the displacement field is epsilon times the electric field. We know that the electric field is minus the gradient of the electrostatic potential. So we can write the Poisson equation as minus del squared psi, or del squared psi is equal to minus charge divided by dielectric constant. Generally, it requires a numerical solution of that equation to understand these 2-dimensional electric fields in MOSFETs. In this lecture, we're not going to be focusing on numerical solutions. We're going to be trying to develop a qualitative understanding for how do these effects play out and what are their consequences. Well, we can understand a lot of what happens just in terms of energy band diagrams. So for example, BT roll-off, or the reduction in threshold voltage as we increase the drain voltage or as we decrease the channel length, can be simply understood by drawing energy band diagrams. This is an energy band diagram of the conduction band versus position from the source through the channel out the drain under low or zero bias. When we apply a high bias, this is what we would like to see happen. We pull the potential down near the drain. We do not change the height of the energy barrier between the source and the channel. That should be controlled by the gate, not by the drain. Now, that height of that energy barrier, of course, is responsible for the leakage current. There will be a small probability that a few electrons can hop over that barrier and go out the drain. That constitutes the leakage current. Now, in a real case, the potential from the drain is going to reach through to the source. And if I increase the voltage on the drain, the potential is going to be pulled down at least a little bit. That little bit lowers the energy barrier. That means that with a lower energy barrier, we get more leakage current, or we get a reduction of threshold voltage, because now, in order to push the barrier down and turn the device on, we need less gate voltage to do that, because it's already been pulled down a little bit by the drain. So we increase the leakage current, we lower the threshold voltage, and the same thing would happen if we would stay at the same drain voltage, but if we would shorten the channel length, that would help the electric fields reach through and pull this barrier down. So we would see the same effects at a shorter channel length also at the same drain voltage. Now, a small amount of drain barrier lowering simply translates the characteristics and does not change the subthreshold slope. But if you get a large amount of barrier lowering, a large effect of two-dimensional electrostatics, you'll see that the subthreshold swing can actually change. So here's an example with some measured data. This is about 100 nanometer channel length, and you're seeing some dibble there in this device. Here is a shorter channel length with the same technology. But you can see on this shorter channel length that you not only have increased dibble, but the slope of the subthreshold characteristic has changed. The subthreshold swing is increasing, which is an undesirable characteristic. The leakage current is increasing exponentially with that increase in subthreshold swing. That increase in subthreshold swing is another consequence of two-dimensional electrostatics that we would like to avoid. Okay. Now, we could have really severe effects when the electric field in the drain reaches through and pulls electrons out of the source, and the current is no longer controlled by the gate voltage much at all. It's very weakly controlled. We would get a characteristic where lots of current flows, even when we apply a small gate voltage. We would say that this device is punched through. The current is flowing from the source to the drain all of the time. On the output characteristics, we might get a characteristic that looks like this. When you see characteristics like this, you know that you have a very bad transistor that really will not be suitable for large-scale circuits, or any circuits for that matter. The physics of punch-through is that we have not just lowered the barrier, but in this case, the effects are so severe, we've completely removed the barrier. So now there is no barrier. Electrons can freely flow from the source to the drain without any help from the gate. This is a severe case of two-dimensional electrostatics, and it's not a useful transistor when it's punched through. Okay, so these are the effects that can occur. When we're designing transistors, our goal is to control these effects. And how do we control these effects? Well, one way to control electric fields is to screen out their influence. So let me remind you of what screening is. So it's easiest, you may have encountered screening in this context. Let's say I have a positive charge in a semiconductor, and this might be an ionized donor. And I have a bunch of mobile electrons that are free to move around in the semiconductor. Well, the positive charge is going to attract the negative charges. The negative charges will bunch up around the positive charge and try to cancel out the net charge. Well, we say that that's screening out the charge. And what we will find is that the potential in this situation is given by something called a screened Coulomb potential. You can see the bare Coulomb potential here, but then there's a factor, e to the minus distance over Debye length, and that is the length over which the influence of that charge decays away exponentially. We call that the screening length, and that screening length is the Debye length in a semiconductor. The more carriers we have to screen out charges, the shorter that screening length is, and that means the influence of stray charges will be felt in only over very small distances. Well, there is another factor, another way to screen charges out and electric fields out, and that is through something that is called geometric screening. So I can illustrate that here with a bulk MOSFET. What you're seeing here is a neutral p-type region. The white regions here are intended to represent depletion regions. We will apply a large electric field to the drain, which means that there will be a positive electric field that emanates from the drain. That positive electric field has to terminate somewhere. And typically what will happen is it will terminate on charges in the depletion region, but it's a complicated two-dimensional problem. Some of those field lines may terminate on charges or at the sheet, at the surface of the metal gate electrode itself. So we might have a situation like this if we solve numerically the two-dimensional Laplace equation or Poisson equation. Now, if we would look at this, we could see that there is a distance, we'll call it capital lambda, over which the electric field is screened out. Beyond that point, we don't see the electric field emanating from the drain. This is a good situation because if the channel length is longer than this geometric screening length, then the influence of the drain potential will not be felt near the source end of the channel, and the barrier will not be pulled down. So this is the kind of situation that the device designer would like to ensure happens. These are numerical simulations of actual solutions to the Poisson equation in a double gate MOSFET that has a very thin oxide of 1 nanometer. You can see the blue electric field lines emanating, and now they're terminating both on a top gate and a bottom gate in this fully depleted structure. And you can look at that and you can see what the geometric screening length is. Double gate structures are actually preferable over single gate bulk structures because they're more efficient in screening out these fields over shorter distances. Now, this has sort of led these issues as channel lengths got shorter and shorter. It became more and more difficult to control these two-dimensional electrostatic effects. Eventually, transistor manufacturers had to switch to completely different designs. So they had to move from the bulk planar MOSFET to a Finfet. A Finfet or to an ultra-thin body SOI transistor. We saw both in the previous lecture. In a Finfet, the silicon channel itself is a thin fin of silicon that stands up vertically. There's a connection to the source on one end and a connection to the drain on the other end. And then there's a gate electrode, and the gate electrode wraps around the fin. So it surrounds the fin on 3 of the 4 sides. That provides very good geometric screening, screens out the fields when we apply a voltage to the drain, and helps us ensure that we do not get much barrier lowering. This is going to work for a while. Already the industry is talking about the need to go a step further to gate all-around structures or nanowire structures where you wrap the gate completely around the channel so that you even more efficiently screen out the electric fields. Well, you can compute that screening length, and what you'll find is if you compute that screening length from a solution to the Laplace or Poisson equation, we usually do these, these effects are seen in subthreshold. We're usually most worried about understanding those effects in subthreshold. So there's no mobile charge, so we can simply include the depleted charge, solve the Poisson equation. Here are a couple of papers where you can see how that's done, the Laplace equation actually. And one of the things you will find is that there may be some screening length for a bulk planar MOSFET. If we put a gate on both the top and the bottom of a fully depleted structure, the screening length is even less. If we use a nanowire device and wrap the gate completely around the channel, the screening length is even less. All of that is desirable because a rule of thumb says that the channel length has to be greater than about 3 of these screening lengths in order to have good electrostatically well-behaved transistors. Okay, so we have talked about various ways of qualitatively understanding the solution to this two-dimensional Poisson equation. One was a barrier lowering argument. One was a geometric screening length argument. There is also a capacitor model of understanding these effects that you might find useful, and you can find that discussed in these notes here. But this should give us an adequate qualitative understanding of the role of two-dimensional electrostatics. Okay, so now we can talk about how in the remainder of the course, we're going to spend a lot of time focusing on the so-called virtual source. The virtual source is the top of the energy barrier between the source and the channel. This is what gives the name to the virtual source model that we've discussed. Now, what makes the virtual source model special is that the slope of the energy band diagram is 0 at that point. The slope is related to the electric field, so it means that the electric field in the lateral direction is 0 at that particular point. It means that our so-called gradual channel approximation, where we assume that the electric field normal to the surface is much stronger than the electric field along the surface, that is well satisfied at the virtual source. So we should expect, since the gradual channel is well satisfied there, for our classic 1D expression for charge versus gate voltage should work at the virtual source. And indeed it does. The virtual source, though the region of interest is a small region around there, this equation is not exactly correct. There is some small influence of two-dimensional electrostatics, but we can include that small influence by making the threshold voltage drain voltage dependent through a Dibble parameter. So the virtual source is a place where this simple, essentially 1D electrostatics with a minor modification should apply. Since we know the charge at that point, it's a good point to ask, how can we calculate the current? Now, I should point out that this really only happens if we have designed the transistor well. Any old MOSFET, this won't necessarily happen. But if the device designer has done his or her job properly and has designed an electrostatically well-behaved device, this is what will occur, and that's what we're after. So this is what we would call a well-tempered MOSFET, in the words of my colleague Dimitri Antoniadis from MIT. A well-tempered MOSFET is one where this simple expression for the charge, mobile charge in the semiconductor, applies at the virtual source with small corrections due to Dibble. It's one in which there is a small region near the gate end of the channel that is strongly controlled by the gate potential and only weakly controlled by the drain potential. And what that means is that as we continue to increase the drain potential, we'll get more and more potential drop near the drain end, but we'll have a very small effect on what happens near the source end, and that's the part that limits the current under high drain bias. So this is what we mean by an electrostatically well-tempered MOSFET. This is the goal of the device designer. So let's summarize. Two-dimensional electrostatics generally degrades the performance of MOSFETs. It leads to things like threshold voltage depending on the length of the transistor, Dibble and subthreshold swing they also depend on the drain voltage. These are not desirable characteristics for a transistor. We'd like to have one threshold voltage. We don't want it changing as we change the drain voltage or as we change the channel length. The goal of transistor design is to make one-dimensional electrostatics apply at the virtual source and design an electrostatically well-tempered MOSFET. And to achieve this, we engineer the MOSFET in a way that the gate has strong control over the height of the energy barrier between the source and the channel, and the drain has a weak control. And that means we try to use geometric screening to minimize the influence of the drain back at the source end of the channel, and that has led in recent years to the move from bulk planar MOSFETs to Finfets, and may eventually lead to a move to gate-all-around or nanowire structures. All right, so we are getting close to the point where we can wrap up in Unit 3 on electrostatics. Now that we have a better understanding of MOS electrostatics, it's time to revisit our virtual source model and see if we can make it a better model. That'll be our topic for the next lecture.